Welcome back to the deep dive. We have a mission today that honestly completely rethinks the hardware sitting in your pocket right now.
Yeah, it really does.
We are unpacking this massive stack of documentation, architecture diagrams, and developer notes from a project called Fit Live Frame AI.
It's a fascinating one.
And the goal here is to really understand how developers are currently solving, one of the hardest physical world problems in computing, which is real-time multimodal analysis.
Right. And the architecture we're looking at today, it really serves as a masterclass in modern system design. It's essentially a blueprint for how to handle continuous heavy data streams.
Like live video and audio.
Exactly, live video audio, without just completely collapsing under the weight of latency.
But before we dig into the actual code and the infrastructure, we really have to establish the mandatory context behind this project.
Yeah, the constraints are key here.
Because everything we're exploring today was built under intense constraints. This entire stack was created specifically as an entry for the Gemini Live Agent Challenge hackathon.
Yeah.
And they targeted the live agents category.
Which is notorious.
Yeah. For you listening, that specific category demands real-time multimodal audio and vision interaction. So they weren't allowed to just build a standard asynchronous app.
No. The hackathon demanded an agent that sees, hears, and speaks concurrently, in real time, with a human user.
Right.
And those hackathon constraints, they're the crucible that forced these specific engineering decisions. When you're mandated to build an agent that processes live video and responds verbally without lag.
Standard web architectures just completely fall apart.
They absolutely do. You have to invent workarounds for the fundamental limits of bandwidth.
And that brings us to the core problem Fit Live Frame AI is trying to solve. Let's look at the scenario they started with. Working out at home is incredibly popular, but it suffers from what the developers call the feedback void.
The feedback void, yeah.
You're in your living room doing squats, deadlifts, kettlebell swings. You might think your form is perfect, but maybe your back is rounding or your knees are caving in.
And without a human trainer standing right next to you, that bad form goes entirely unnoticed.
Exactly. And repeating bad mechanics under heavy loads, that's just a fast track to chronic injury. So the mission was to turn a standard smartphone into a real-time, 3D vision-powered sports lab to fill that feedback void.
And the output of their solution is a system that generates a shadow mentor.
A shadow mentor, I love that term.
It's great. It's a 3D digital twin, basically a skeletal avatar rendered on your screen that perfectly mirrors your physical movements in real time.
So if you dip your left shoulder...
The digital twin dips its left shoulder instantly.
Wow.
And powering that visual interface requires a highly orchestrated, lightning-fast backend, utilizing a massive array of Google AI models and Google Cloud services.
So let's start with the central antagonist of this entire project, multimodal latency.
It's the biggest hurdle.
Right. When we look at standard AI video analysis, there's a massive bottleneck. A typical model takes anywhere from 2 to 4 seconds to ingest a video frame, process the visual data, generate a response, and then send it back to the client.
Right.
If we apply that to the fitness scenario, a 4-second delay is catastrophic. If your knees cave in at the bottom of a squat and the AI takes 4 seconds to warn you...
So you've already finished the rep.
Yeah, you've racked the weight and potentially torn a meniscus.
Exactly. Standard HTTP request and response protocols simply cannot survive in a live physical environment like that.
Because the standard architecture requires the user to submit a payload, wait for the server to process it, and receive a response.
Right. So to bypass that, the team integrated the Gemini Multimodal Live API utilizing bidirectional, or BD, streaming.
We see BD streaming popping up more and more in high-performance applications.
It's becoming the standard for real time.
Yeah. In this specific stack, they bypassed standard REST APIs and implemented a WebSockets architecture. So instead of a ping-pong match of data, they open a continuous two-way tunnel between the user's mobile browser and the AI processing engine.
The client device is constantly pushing a stream of video frames and audio up the pipe, while the AI is concurrently streaming analysis, coordinates, and verbal feedback down the exact same pipe.
So neither side is waiting for the other to finish a turn.
Exactly. By keeping that WebSocket connection open, they slash the round-trip response time to under 200 milliseconds.
Under 200 milliseconds.
Yeah. And biologically speaking, 200 milliseconds feels instantaneous to human perception.
That's wild. But that real-time connection is really just the delivery mechanism, right?
Yeah.
The actual intelligence processing the data is incredibly fragmented.
Highly fragmented.
They didn't rely on a single monolithic AI model to do everything. They built a highly specialized roster. The documentation highlights Gemini Flash as the primary engine, and they iteratively deployed versions 1.5 through 3.1.
Deploying Flash as the core brain is a very deliberate optimization for speed.
Because Flash is built for that.
Right, Flash is engineered specifically for high-frequency, low-latency request cycles. In the context of the Shadow Mentor, Flash is analyzing the incoming WebSocket frames, calculating the travel distance of your joints in three-dimensional space, and mapping your form precision.
It's basically operating as the fast twitch muscle of the system.
Exactly. A heavier, more parameter-dense model would completely bottleneck the real-time feedback loop.
But Flash is operating in the moment. It's built for reflexes, not necessarily long-term memory.
Right.
Over the course of a 45-minute workout, it's ingesting tens of thousands of frames. It can't possibly synthesize all of that historical data efficiently while still maintaining that 200-millisecond reflex speed.
No, it would crash.
Yeah.
And that is where they hand the baton over to Gemini Pro.
Again, utilizing versions 1.5 and 3.1.
Right. The architecture splits the cognitive load. If Flash is the spotter reacting to your current rep, Gemini Pro is the analytical head coach reviewing the game tape.
I like that analogy.
The developers leverage Pro specifically for its thinking level high mode.
Ah, okay.
So once the WebSocket connection closes at the end of the session, Pro ingests the aggregate data to generate comprehensive shadow reports.
So it's analyzing your fatigue degradation over the 45 minutes.
Yes, identifying microscopic patterns in your form breakdown and compiling actionable strategic takeaways for your next session. It handles all the asynchronous heavy lifting.
That makes perfect sense. Now, there is another really compelling layer to this orchestration. The documentation details a specific interruption logic called the roadblock.
The roadblock is brilliant.
Let's go back to the deadlift scenario. Flash is monitoring your form in real time. Suddenly, it detects your lumbar spine rounding under the load.
Which is an immediate safety hazard.
Right. The system is programmed to trigger a roadblock. It physically halts the 3D digital twin on your screen, interrupting your set.
But it doesn't just give you a text warning.
No. It triggers a completely different model, VO 3.1.
Triggering a generative video model mid-session is a fascinating architectural choice.
It really is.
The moment you hit a roadblock, VO 3.1 dynamically generates an 8-second high-fidelity 4K instructional clip.
So it shows you the fix.
Exactly. This clip demonstrates the absolute perfect biomechanical form for the specific movement you were failing at. You aren't just reading a prompt telling you to straighten your back. The system is synthesizing a custom visual demonstration of the correction on the fly.
And doing this without breaking the user's flow state is crucial. Working out while staring at a silent screen reading text prompts is a terrible user experience.
That was the worst.
Environmental audio is a massive part of gym culture. To solve that, they integrated Lyria 3. But this isn't just a static Spotify playlist. They routed Lyria 3 through the real-time API to generate dynamic 48 kilohertz stereo workout music.
And the brilliance of the Lyria integration is how it closes the multimodal loop.
How so?
Well, the application is already calculating the velocity of your movements, right?
Yeah.
How fast you're executing reps.
Right, through Flash.
Exactly.
Yeah.
That velocity data is fed directly into Lyria 3. The generative music engine then syncs its tempo, its BPM, directly to your physical movement speed.
No way.
Yeah. If you accelerate into a sprint or push harder during a set, the music mathematically increases its tempo to match your physical intensity. The environment reacts to your output.
It's an entirely reactive ecosystem. That's
Yeah.
incredible. And just to round out the AI roster, they utilized a model with, honestly, my favorite naming convention in the entire stack, Nano Banana 2.
Nano Banana 2.
It's a lightning-fast generative image model. They trigger it post-workout to render custom victory posters. It takes the metadata from your session, your 3D avatar pose, and generates stylized graphics for social media sharing.
And a very clever engagement loop built on top of the heavy analytics.
So we have this massive array of highly specialized models: Flash for reflexes, Pro for reasoning, VO for video generation, Lyria for reactive audio, and Nano Banana for images.
Right.
But all of these AI endpoints are essentially just APIs. Orchestrating them, maintaining state, and routing the data requires an incredibly robust infrastructure.
The models are the intelligence, but the cloud architecture is the nervous system keeping the application alive.
If we look at the documentation, it points to a completely serverless backend built on Python and FastAPI.
which is necessary for a project like this.
Yeah, for a hackathon project that might suddenly scale from 0 to 10,000 concurrent users upon public release, hard-coding server capacity is a death sentence.
Exactly. So they containerized the entire backend infrastructure and deployed it on Google Cloud Run.
Cloud Run.
Cloud Run is the optimal deployment environment for this specific workload. By containerizing the Fast API backend, they've isolated the application logic.
Right.
And Cloud Run allows that container to remain dormant when traffic is zero, incurring no compute costs.
Which developers love.
But the moment a wave of users logs on at 5:00 p.m. for their post-work gym session, Cloud Run instantly scales horizontally. It spins up thousands of container instances to handle the WebSocket's traffic. The developers never have to provision or manually manage the underlying server instances.
But horizontal scaling doesn't solve the orchestration problem, does it?
Yeah.
You have raw 4K video coming up the pipe, generative music streaming down, JSON coordinates firing every few milliseconds, and multiple LLMs passing context back and forth.
It's a traffic jam.
Managing the traffic between all these microservices is incredibly complex.
And that complexity is managed by the Google Agent Development Kit, or ADK.
The ADK.
The ADK functions as the central nervous system of the architecture. It orchestrates the live queue of multimodal data streams and manages the agent's specific tool calls. It determines when to route data to Flash versus when to trigger VO.
And the ADK implementation actually solves a very specific, incredibly annoying physical world problem, the gym Wi-Fi drop.
Oh, everyone knows that one.
Anyone who works out on a commercial gym knows the connection in the weight room is notoriously unstable. If you are relying on an open WebSocket connection and your phone drops Wi-Fi for 3 seconds, standard applications will just terminate the session.
And you lose your rep count, your calorie burn, your form history, everything.
Exactly.
But the ADK provides a feature specifically called session resumption.
How does that work?
It allows the backend to securely hold the current state of the application in memory. If the client device loses connection, the ADK just pauses the incoming data queue.
It just waits.
It waits for the handshake to reestablish.
Yeah.
And the moment the phone reconnects, it resumes the session exactly where it left off. The state isn't lost. This prevents transient network failures from destroying the user's workout data.
That's a lifesaver. And speaking of that data, they are generating massive amounts of it. Video files, coordinate logs, performance metrics.
Tons of data.
They split the persistence layer into 2 distinct Google Cloud services. For the heavy, unstructured data, like the raw session recordings and the VO-generated instructional clips, they utilize Google Cloud Storage.
Which is highly efficient for blob storage.
Right.
But you cannot query cloud storage fast enough to populate a live user dashboard.
It's too slow for that.
Exactly. So for the structured data, the historical rep counts, the precision scores, the calorie trends over a 6-month period, they route that to Firestore.
Firestore.
Yes. Firestore is a NoSQL document database that maintains real-time synchronization with the React front end. When Gemini Pro finishes its post-workout shadow report, that JSON payload is written to Firestore, and the user's dashboard updates instantaneously.
Now, there's one infrastructure decision in this stack that I find fascinating because it addresses a major vulnerability in generative AI, hallucination.
Oh, yes.
We have all seen LLMs invent facts with complete confidence. But if you are building an application that provides physical, biomechanical advice, a hallucination is physically dangerous.
It's a liability.
If the shadow mentor hallucinates and tells a user to aggressively lock their knees at the top of a heavy leg press, that user is going to end up in the emergency room.
You cannot rely on the native weights of an LLM for medical or biomechanical accuracy.
So how did they fix it?
To neutralize the hallucination risk, the developers implemented a strict grounding architecture using Vertex AI vector search.
Walk us through how that grounding mechanism actually intercepts the AI's response before it reaches the user.
Well, they compiled a massive data set of verified professional athletic guidelines, physical therapy protocols, and biomechanical safety standards. They embedded this text and stored it as an index within Vertex AI vector search.
Okay, so they have a verified database.
Exactly. So when Gemini Flash or Gemini Pro generates a piece of form correction or strategic advice, that output is essentially quarantined.
It doesn't go straight to the user.
No. The system queries the vector search index to cross-reference the AI's intended response against the approved medical database. If the AI's advice conflicts with the established safety standards in the vector database, the response is blocked or rewritten.
Wow.
It ensures the athletic intelligence is anchored entirely in verified science, not probabilistic text generation.
It's essentially forcing the AI to pass an open book medical exam before it's allowed to speak to the user.
Yeah, that's a great way to put it.
So that covers the cloud infrastructure. Let's dig into the actual engineering hacks, because this is where the developers had to get incredibly creative to bridge the gap between cloud AI and local browser rendering.
The front-end challenges were huge.
The fundamental challenge here is translation. Gemini is a cloud-based model that outputs data, but the shadow mentor on the user screen is a 3D skeletal avatar rendered locally using React and Three.js.
And the friction here is that LLMs are inherently conversational. If you ask a standard model to track your hand during a bicep curl, it wants to reply with conversational syntax. It wants to say, "Great job, I see your hand is currently at position X and Y, keep it up."
Which sounds nice, but
But a 3D rendering engine like Three.js cannot parse conversational English. If you feed conversational text into a skeletal rendering rig, the application will instantly crash. The 3D engine expects pure mathematical floats.
so how do you force a highly conversational model to just shut up and give you the math?
The developers utilized a highly constrained prompt engineering technique they named strict JSON thought signatures.
Strict JSON thought signatures.
Yes. In the system instructions, they explicitly stripped the model of its conversational abilities. They commanded the Gemini model to output nothing but atomic JSON packets.
Oh, no chit-chat.
None. Every single response is formatted strictly as structured data containing precise Y and X coordinates mapped on a 0 to 1,000 scale.
So there's zero conversational bloat traversing the WebSocket. It's just a relentless stream of mathematical coordinates mapping the user's head, hands, and feet.
Exactly. The React front end catches that JSON packet, parses the 0 to 1,000 scale data, and maps those precise coordinates directly onto the skeletal joints of the Three.js rig.
And because it's so small.
Because the payload is stripped of all text and formatting, it is incredibly lightweight. This allows the digital twin to mirror the user's physical body in perfect, fluid synchronization. The visual interface is literally rendering the AI's internal mathematical logic in real time.
That constraint is just brilliant. Now, let's look at one final massive hurdle they had to clear. They call it the infinite video fix.
This is my favorite part of the stack.
The application allows users to upload existing pre-recorded workout videos for the AI to analyze.
Right.
Let's say a user recorded an hour-long powerlifting session. That raw video file could easily be 7 gigabytes. If a mobile browser attempts to execute an HTTP request to upload a 7 gigabyte file to a cloud API, the browser will likely run out of memory and crash.
Or it'll just hit a payload limit and timeout.
You simply cannot push that much raw data from a phone efficiently.
The standard approach to file uploads fails completely at that scale.
So what's the workaround?
The engineering solution here is a masterclass in edge computing. They shifted the processing burden away from the network and onto the user's local hardware. Instead of attempting to upload the massive raw MT4 file, the React front-end handles the data ingestion locally using a heartbeat interval.
Okay, explain the mechanics of this heartbeat. What is the browser actually doing while the video plays?
A background timer is initialized in the browser, ticking at a set interval, say, every few hundred milliseconds. When the user hits play on their local 7 gigabyte video, the heartbeat activates.
Oh, okay.
On every single tick, the front end reaches into the video player and draws the current frame onto a hidden HTML canvas element.
A hidden canvas. So the user never sees this canvas.
Exactly. It exists purely in the background, Dom.
The browser is just silently extracting static screenshots from the moving video. But wait, a 4K screenshot is still a massive file to send to an API continuously.
Which is why the canvas immediately runs a compression algorithm. It checks the dimensions of the extracted frame. If it's a massive 4K image, the front end downscales the canvas width to a maximum of 1280 pixels.
Okay, that shrinks it down.
And then it converts that downscaled image into a base 64 string.
Oh. So instead of wrestling with a bulky multi-gigabyte file upload protocol, they were converting the visual data into lightweight text strings.
Exactly. They transformed a catastrophic bandwidth bottleneck into a highly compressed, continuous stream of text. That base 64 string is what gets fired across the WebSocket to the Gemini API.
That is so smart.
But they implemented one more layer of fail-safe logic on top of it. a pending frame queue.
Right, because what happens if the user's internet connection degrades, but the local browser is still extracting frames at 60 frames per second?
The browser would overwhelm the network and spam the API, causing a rate limit crash.
So the queue stops that.
Yes. The pending frame queue intercepts the base 64 strings. If the API is taking too long to respond due to network latency, the front end holds the newly extracted frames in a waiting line.
It just buffers them.
It paces the transmission based on the network's actual capacity, ensuring a smooth, crash-free analysis regardless of whether the video is 1 minute or 1 hour long.
It's just phenomenal client-side ingenuity. They solved massive bandwidth, memory, and latency issues before a single byte of data ever left the user's physical device.
It really is elegant.
And this entire architecture is why FitLife Frame AI is so much more than clever hackathon entry. It is a highly optimized blueprint for the next generation of applications. They proved that by combining purpose-built AI models, Flash for real-time velocity, Pro for asynchronous reasoning, VO and Lyria for reactive generative media.
And anchoring it all on scalable infrastructure like Cloud Run and Firestore.
Yes, you can solve intensely complex physical world problems.
The direct application for anyone analyzing this stack is that these engineering principles are entirely agnostic.
They apply anywhere.
Exactly.
Yeah.
Bidirectional streaming to bypass HTTP latency, strict JSON prompt constraints to turn an LLM into a deterministic programmatic controller, local canvas processing to bypass upload bottlenecks. These aren't just tricks for a fitness application.
Right.
These are the foundational mechanics required to build systems that interact with the physical world in real time. We're transitioning from a paradigm where AI processes static text to a paradigm where AI actively observes and reacts to live physical environments.
Which leaves us with a truly fascinating implication to consider for you listening. We now have the architectural blueprints to string together multimodal models that can map your skeleton in 3D space, calculate your joint velocity, dynamically alter the tempo of your environment, and physically correct your posture with less than 200 milliseconds of latency.
It's here today.
The latency war is actively being won. So if an AI can do all of that simply by watching you through a standard smartphone lens, if it can do that just through a lens, what other physical, real-world skills could it teach you?
The possibilities are endless.
Think about the mechanics of learning to play a violin, or the precise hand placements required for CPR, or the exact swing path of a golf club. The camera on your phone is no longer just a sensor for capturing static memories. It is rapidly becoming an active, hyper-intelligent mentor, something to chew on the next time you open your camera app. Thanks for joining us on this deep dive. We'll catch you on the next one.